Okay, let's tackle the second question in functional programming. So we have the data type tree defined below specifies a type of binary tree where non-empty nodes can be colored red or black and contain integer values. So we have below here we have data color is equal to red or black, deriving equality, and type value is equal to integer, data tree is equal to empty for color tree, value tree. Okay, that's pretty standard. These are just the data types we define. Part A, explain the role of the keyword deriving, 2 marks. So for this, deriving keyword is essentially used to make a data type an instance of a standard type class. So what it does is that it tells the compiler to do so automatically. Like we don't want to define it ourselves, so we just tell them, okay, you should derive it from that, and you're just an instance of a standard type class. And then in part B, or that's like the big part where 15 marks are allocated, we're supposed to write programs for 3 invariants. A red node does not have a red child. Every path from the root to empty node contains the same number of black nodes, and for any node for color left I, right, the value I must be greater than any value in left and less than any element in right. So this is a binary search for each of the 3 variants above. Write a Haskell function type of tree to bool that checks whether the input tree satisfies the corresponding invariant. For full marks, each question function should run in linear time. Okay, so basically the idea behind this is we write 3 invariants. So we're going to start off with the first one. Red node does not have a red child. Okay, that's pretty straightforward. If we want this to hold true, and that every other function is we're given the tree, and then we would just want to test if it's true or false. This is just a function we're trying to write. And then we have then the invariant that it holds all the time. So for the first one, red node does not have a red child. We're gonna first write a helper function. This type of question, it's kind of clean to either write a helper function that gives you more values than you need, more information, or it just kind of takes in more parameters so then you can actually manipulate it to what you need. So inside here is red. We define a function to be a tree to bool, and then what we do is we just check. We usually it's in the form of fork, color, tree, value, tree, right? So right now we're only caring much about the value. So if the thing is red, then we just return true. If the thing is not red, then we just return false. So this saves the trouble of actually like checking the value. So then we can just write is red, and then we know if it's red or not. So that's just basically what we're doing here. And then what we have is the actual invariant of checking if it's the child does not have a red child. Like the red node does not have a red child, we do it this way. We call it invariant 1, takes tree to bool, like we say. If it's empty, like we have nothing inside, it has to be true, trivially true. And if we have this of the form color, then tree on the left side, then the value, then the tree on the right-hand side, then we have to kind of check that the invariant of 1 holds on the left tree, right? The left tree has to be true. The right tree also has to be true. And then we check our tree current node if it works or not. Our current node works. If it's not red, then obviously, by all means, there's even no point saying anything because if the color is red, then not red, then it's true. If it is red, then here we say not is red. So that is the other case. And then we want to check, make sure that the child on the left and on the right are, what is it called? Not red. So we make sure that this condition, the invariant holds. So the idea is always, for these type of questions, we have usually just think of it as this. We have our node. We have to first make sure that the left-hand side works. So we want to check this, then check the right-hand side holds, then check that the node holds by checking its comparison with the left and right child. So that's what essentially we do here. I think this is a pretty straightforward thing, and it's Owen for sure, because we only go through each one once. We just check that's true, it's true, it's true. Okay, for the second one, we have every path from root to empty node contains the same number of black nodes. So we want to make sure the black nodes is the same. So for this idea, it's the sense that if I have a node, at any node, if I have leaves, then the leaves should always be the same number, or else I would get different because every path on the top would be the same, right? Because you get to this point, you want every path to be the same. So the node of the number has to be the same as well. So that means that every time we have to check, okay, the left-hand side, the right-hand side are the same. That's what we're trying to do. So the type of invariant 2, then we put in the tree, which we just call T, and then we write a helper function so that our code actually looks nice. So we want to check height, and then we want to make sure that our T does not equal nothing. So that means we don't have an error. So our check, if we have a empty, that's just trivially true because we don't have any branch. So we're just going to say just 0. Next, what we have is our check height, and then we start the recursion. We have our fork of CLVR from before, and then we just have a do statement. So we first check, okay, on the left-hand tree, what is the height, right? We want to check the height. And on the right-hand tree, what is the height? If the left-hand tree and the right-hand tree have the same height, then we can say that it's just the HL plus if we just return just, and the HL plus if CC equals black, then 1 else 0. I think that's pretty straightforward. It's just checking if it's the case. Otherwise, it's just nothing, which is just an error that it's not possible. And because we know once we get nothing, then it would always return nothing, because if there's an error, then it doesn't work out right. And in the just statement, we have HL plus if equals C equals black, then 1 else 0. So this just essentially increments the thing so that HL is because our HL and HR are already checked to be the same, then it doesn't matter what we have. We just take one branch of it and then we just check the node if it's black or not. If it's black, then we add 1. If it's not, then it's 0. So then we get up to this point. So we get the branch up to that point. So that's how we do it. For invariant 3, we're going to be looking at for any node, fork, color, left, I, right, value I is greater than element in left, I is smaller than element in right. So this is just a classic binary search tree like construction where we split off the values. So what we have to do here is we first input our tree, and then we write also a helper function because it would be too messy otherwise. So we have check, and then we define check to be, we put in 3 parameters. Check nothing, nothing t. Why do we do that? Because inside here, we first write check, and then we don't really care about what the front value is. If the tree is empty, then obviously it's definitely trivially true that it's split apart by the element. No, because there's nothing inside. Next, we keep track of our minimum value and our maximum value in the place. And then the tree should have the fork, and we don't care about the color in the sense. So we have our LV and our value left tree and right tree. So then we start with a bunch of conditions that we check. So first we check the maybe, if it's true, v if v is greater than minimum of v. So basically in our tree, like let's say we have this tree, right? Let's call this is our v, this is our left tree, and this is our right tree. Okay, so basically if our v is greater than the minimum of v, then If our v is greater than minimum v, then it would mean what was my thought process that time? Why would I want minimum and maximum? Um, but I'm gonna make sure I search this up. I'm kind of having trouble remembering why it's the case. Question 2, the invariant. But just to explain here, the maybe function that I'm using here is lowercase because it's a function. So we have first, the first parameter is the default value. So inside here we set it to be true. Then we have a function that we input in, and then we have our input. So basically what this means is v greater than, and then our input is min v. So it would just be, the equation would just be v is greater than minimum v, and so on and so forth, with v is smaller than maximum v. And then next is check minimum v, just vl. So basically what this one, I can definitely explain this one and this one. These two are pretty straightforward. It's just checking that the left tree has to be smaller than v. That's just by definition because we're just checking that minimum v is less than our current value. But I the chat Gemini is not giving me a good response. Let me go send my code directly. Okay, it's definitely been a long time. My brain is not working in the morning, but mm, guess it's a good thing that I'm recording this video so that you're kind of figuring things out as I go along. Okay, I'm still trying to figure out what it means. Give me a sec. Okay, this is what Gemini said. Kind of paste over this. So this is what it said. Move it over here and let's talk about. So over here, the whole point of having the check is that we have our min v, max v, and our fork. So we first want to check four conditions: the lower bound, the upper bound, the left child, and right child. If it's lower than the upper bound, like um, so inside here, the first one may be true, v greater of me min v. So we want to check, is v greater than the minimum limit? If it's minimum is v is nothing, so we don't have a limit, then it returns true. Otherwise, it would just check that we are indeed within the bounds. The same with max, except it's smaller than, so we're within the bounds, and it's the same if nothing is true. Not if it was initially not initialized, so then it would just be nothing, so it would be true by default. Next, we have the check statement, which is the minimum v, just v. This is to update, check the left child and update the max. So our check function should give us whether or not it's true and what the minimum. Yeah, I'll paste something over so that it also helps, because without the thing, it's kind of hard to explain. So, here we have the recursive calls, the check and check. I think this is just what sets the constraints, so that's more clear. So we have check min of this just VL. So we go to the left subtree, and we know that they're smaller, so we're going to update the minimum. So we know that. Okay, never mind. I'm getting my logic mixed up. We want to change the boundary so that because we're walking into the minimum tree, then we are trying to set up a maximum boundary, because we know that this is a sorted thing because everything on the left has to be smaller. So this, our node where we left, if we go to the left subtree, is our maximum value, and that should be our max fee. So that's our new upper bound. And the lower bound still remains the same as before. So check min v fork of max listing. When we go to the left subtree, we know that it's smaller, so when we go that, yeah. And then the lower bound is because we just kind of changed minimum v as from before, and then the maximum is changed to just v, because that's like the starting point. And then we have our L, which is our left subtree. Okay, that makes a lot more sense. Okay, now I can explain the whole thing. Now I kind of remember how it works. So essentially, the idea behind the check is that we have three parameters. The first one is just our current minimum values, our boundary on the minimum. Then we have our boundary on the maximum, and then we have our current tree, which is the fork, and then we have the color, which we don't care about, the left tree, the value, and then the right tree. So that's what the first line means. And then what we do is we do want to keep track of the moving left and right boundaries, as well as if we want to update that current thing. So then we go down the tree. So first we check the boundaries. The first two statement checks the boundaries. May be true v greater than min v. So that basically what it checks is the lower bound, because when v is greater than min v, that's when it's true. If it's less than that, then we know we're problematic. We're kind of out of bounds. And if it's nothing, then it's set to be automatically true. And the same with the upper bounds reversed. And then next we have the statement check min v, just VL. So what this does is that it calls this thing. And then we call it with min v, and then our maximum boundary is updated by our current node because we're walking to the left, and everything left of this node has to be smaller than this current node. And the same reasoning with the right-hand side, except the minimum value is updated. So we just put just v over here. Okay, that makes a lot more sense. Okay, so that's invariant 3. And then moving on to part C, write a program of type tree that will generate an infinite tree with the following properties. Note that it's not a red-black tree. Tree does not contain any empty nodes. The sequence resulting in the BFS traversal of the tree is 0, 1, 2, all the way all non-negative integers. Even number nodes are black, all number ones are red. Okay, so basically the idea is that the tree looks something like this, where our node is 0, and then we go 1, and then 2, then 3, then 4, 5, 6. So we're essentially filling up the tree by row of the numbers, like in sequence. And then the odd ones are red, the even ones are black. Okay, so how we're going to generate this is that we see that the children of n are n plus 2 and n plus 1. Because, for example, 0 is 1 and 2, 1 is 3 and 4. So it's basically it's kind of like a binary tree. So you're going to move down 1, which is you have to multiply it by 2. And we see that the next one is plus 1 and plus 2. So that's how we got this. So then we're going to write infinite tree is just a tree. We're going to just write a helper function, generate 0. Or generate of n is going to be a fork, so it's obviously going to be a tree. And we're going to help with color. We're going to determine color. That's also going to be a helper function to make it simple because it's either going to alternate between even and odd numbers. And then we want generate 2 times n plus 1, and then our current value n, and then we want to call this function again for generate 2n plus 2. So that's just basically where we got this recursion from. And then for our color, we know that if it's even, then we do black. If it's otherwise, which is odd, then it's red. So that's pretty straightforward. Okay, so that's the end of this problem. I think this problem, the difficulty in this problem is actually not the syntax, but just like actually being able to understand what it's asking for, what the data types are, how to do the binary search, and the invariants, how to actually write up the code and use auxiliary functions so that it actually looks nice and easy to read. It's kind of hard to get, it's kind of easy to get lost in the middle of the logic, but I think relatively the recursion logic is okay. And then invariant 3, I was a bit lost, but afterwards I kind of get, okay, yeah, boundary, boundary, update, boundary, update, boundary. Great. That's pretty simple. Let's end off here. Let's open Zoom.